Would the death of our universe cause another Big Bang? Or would everything simply fade into a silence so complete that even time forgets how to move? If explorations like this bring you a moment of calm, and if you enjoy drifting through these quiet scientific journeys, you're welcome to gently like or subscribe, only if it feels natural to you. As you settle into whatever stillness surrounds you now, imagine the universe not as a static backdrop, but as a living process, aging in slow motion. Everything around you, every star, every galaxy, every atom in your body, is participating in that gradual aging. The cosmos expands. Light stretches into colder wavelengths. The structures of matter slowly unravel. And somewhere far beyond the horizon of what you can see, distant galaxies slip away faster than the light they emit can ever reach you, as though the universe is quietly turning off the lights one by one. You lie here in a moment that happens to fall in the bright, youthful era of cosmic history. But the universe itself is older than imagination can easily hold, and the question of whether its death could ignite another beginning reaches into the deepest frontiers of theoretical physics. To follow that question, you drift back to the first breath of our universe, when everything that now exists was compressed into a single, unimaginably dense state. Physicists call it a singularity, though the word feels too sharp, too certain for what that moment truly was. It wasn't a point in space. It was the birth of space. It wasn't an explosion inside emptiness. It was the emergence of emptiness itself. And from that trembling origin, the universe expanded, cooled, diversified, sculpting galaxies like gentle eddies in an ancient river. Stars formed, burned, died. Black holes emerged like silent anchors in the cosmic fabric, bending space-time around themselves. Eventually, creatures arose on a small blue planet, capable of asking questions about beginnings and endings. Now, imagine the universe far ahead in its timeline. Stars burned out, galaxies thinning into cold, orphaned systems, black holes evaporating through Hawking radiation, releasing the last whisper of structure into the void. This is the heat-death scenario, a slow, inevitable drift toward equilibrium, where nothing changes because everything has reached its maximum entropy. No more gradients, no more energy differences, no more motion in any meaningful sense. But the question that lingers in the quiet is whether this fading end state could ever curl back in on itself, collapsing, tightening, becoming dense enough to spark something new. The idea of a cyclic universe, one that breathes out in expansion and breathes in through collapse, has appeared in many variations throughout the history of cosmology. Some models, like the oscillatory universe, suggested that after expansion ends, gravity eventually reins everything back together. Space contracts. Galaxies fall toward each other. The fabric tightens until the universe becomes hot and dense again, setting the stage for another Big Bang. For a long time, that idea had an elegant simplicity. But then came the discovery that the expansion of the universe is accelerating, driven by something physicists call dark energy. It acts like a pressure built into the vacuum itself, pushing galaxies apart faster and faster over time. If dark energy remains constant, contraction will never come. If dark energy grows stronger, the universe could end in a big rip, too torn apart to ever collapse again. And yet, if dark energy is not constant, if it is a temporary condition or a phase we do not yet understand, then the story shifts. In some speculative models, the accelerated expansion is only one chapter. Dark energy could eventually decay, fade, or transform, allowing gravity to dominate once more. If that happened, the universe might begin to contract, slowly at first, then with increasing intensity. Galaxies would draw together. The cosmic background radiation would heat up. The cooling, drifting structures of a nearly dead universe would fall inward toward a final convergence. This collapsing state, sometimes called the Big Crunch, could mirror the density of the early universe. And at that moment of ultimate compression, quantum gravity might take over, the domain where general relativity and quantum mechanics merge. Though we don't yet know the correct theory describing this regime, several candidates exist: loop quantum gravity, string theory, and various quantum cosmology frameworks. Many of them hint at something remarkable. A collapsed universe may not end in a singularity. Instead, the dense core could bounce, rebounding into an expansion phase, giving rise to a new universe with its own physical constants, its own laws, its own cosmic story. The idea is subtle and delicate, like watching the universe inhale after holding its breath for longer than time itself. In loop quantum cosmology, for example, space-time has an underlying discrete structure. As the universe contracts, the density eventually reaches a critical threshold set by this quantized geometry. At that limit, gravity becomes repulsive instead of attractive. The universe rebounds. Expansion begins again, a new Big Bang seeded by the ashes of the old cosmos. You can imagine it like a cosmic heartbeat, not in a literal sense, but in the gentle rhythm of expansion followed by contraction, followed by expansion again. But unlike a simple repeating loop, each cycle could be slightly different. Conditions might change. Constants could shift. The physics of the next universe might not mirror our own. In some theories, information from the previous universe could imprint faint traces on the next. Not memories, but patterns, subtle fingerprints encoded in the large-scale structure. And yet, it's equally possible that our universe may never contract. If dark energy persists or grows, then the cosmos stretches into an eternal freeze. In that case, what could trigger a new Big Bang? Here, the story takes on another layer of depth. Instead of a global bounce, new universes may arise as localized events. Far out in the deep future, long after everything has faded, quantum fluctuations might seed new regions of space-time, small pockets that pinch off from our universe and inflate into their own reality. This is the idea behind eternal inflation, the notion that the fabric of space-time can generate baby universes, each beginning with its own Big Bang, each drifting apart from the others, disconnected forever. In that view, the death of our universe isn't the grand trigger of the next one. Instead, universes bloom continuously in a vast cosmic landscape, like quiet sparks emerging in an endless, timeless dark. Here, the parent universe may fade quietly while its offspring expand with their own laws and dimensions. It is a multiverse not of parallel copies, but of continually arising pocket realities, all born from quantum fields at the edge of what can be described. Still, another perspective lingers in the space between these theories, one that considers the universe as a quantum object. In quantum cosmology, the universe can tunnel between states. Even a dying universe, drifting toward maximum entropy, might still undergo transitions in its fundamental fields. A vacuum decay event, for instance, could transform the structure of space-time into a new configuration, releasing immense energy that would resemble a Big Bang inside the expanding bubble of the new vacuum. This wouldn't destroy the old universe so much as overwrite the region it occupies, turning old space-time into new conditions that evolve into a new cosmos. You can imagine it like a small region of the universe flipping to a different quantum rule set, then swelling outward at the speed of light, carrying with it a new beginning. Our universe would not deliberately cause this new Big Bang, but it could set the conditions in which it naturally arises. Even the slow heat death, a universe at perfect equilibrium, might permit rare fluctuations, tiny sparks in the thermal emptiness that eventually grow into entire universes. In physics, even near total stillness contains the possibility of emergence. And so you drift here, suspended between the death of everything and the birth of something new. Whether the universe breathes again through contraction, through quantum tunneling, through inflationary budding, or through processes we haven't yet imagined, the cosmos appears to resist the idea of absolute finality. Endings blur into beginnings. Collapse curls into expansion. Silence incubates creation. As you let the idea settle, you can feel the strange comfort it carries. The universe that nurtures your existence is not a singular event, but part of a larger story, a wider fabric of cosmic evolution that extends beyond any one beginning or any one end. The question of whether our universe's death could ignite another Big Bang becomes less of a definitive puzzle and more of an invitation to understand reality as a continuous process, a cycle of transformation at scales so vast they feel almost tranquil, and in that calm you sense the profound quiet of cosmic time, a rhythm so slow and deep that your own thoughts feel like ripples on the surface of something ancient and luminous. The universe expands, it cools, it changes, and whether it collapses, bounces, buds, or tunnels into something new, the story continues, always unfolding into deeper mystery. But if a universe can end, what exactly is ending? Is it space? Is it time? Or is it merely the version of physics we happen to live inside, dissolving to make room for something new? You feel that question drift across your awareness like a soft ripple, and as it settles, a new one rises beneath it. If a new Big Bang were born from the ashes of this universe, would it remember anything of us? Would any echo of our galaxies, our atoms, our thoughts survive that crossing? Or does each cosmic dawn begin as a blank, untouched sheet of space-time? These questions linger with a quiet weight, and you follow them deeper, as though you've stepped into a vast hallway of possibilities. Each one glows with a different interpretation of what an ending truly means. You imagine yourself drifting forward, not through space but through the long story of cosmic evolution. Somewhere ahead lies an era where galaxies have faded into ghost-like smudges, so distant that their light never reaches anything else again. And farther ahead lies a time when even black holes, once the great anchors of galaxies, evaporate into faint radiation. By then, the universe is not a place full of things, but a thin ocean of nearly nothing. Some call it darkness, but really it is an even quieter kind of light, stretched beyond red, beyond infrared, into wavelengths so vast they barely exist. In that distant future, what could possibly spark a new beginning? Another question rises inside you like a gentle tide. Does the universe need a collapse to restart, or does it simply need instability? You move through that thought slowly, feeling it expand. In the classical picture, everything must contract into a dense, hot core for a new expansion to emerge. Gravity pulls inward. Temperatures soar. The cosmic fabric tightens until another bang erupts. But if dark energy keeps pushing outward forever, collapse never comes. So could something else, something smaller, more subtle, create the conditions for the next universe? You visualize the vacuum itself, not as emptiness, but as a restless sea of quantum fields humming below the threshold of existence. Even in the silence of heat death, that sea never stops flickering. Particles flick in and out of being. Fields ripple with possibility. And once in an unimaginable span of time, one of those fluctuations might gain enough energy, enough coherence to inflate into a whole new cosmos. It's like imagining a tiny spark drifting within an endless ocean of stillness. One spark that grows, expands, stretches space-time in every direction until it becomes a universe of its own. And then another question gently settles beside it. If new universes are continually budding from the quantum foam, is the death of our universe really the end, or merely a quiet chapter inside a much larger landscape? You drift deeper into the vision of that landscape, that cosmic field where universes are not isolated stories, but expressions of an ongoing creativity woven into the fabric of reality. A multiverse that doesn't exist parallel to us like mirrored rooms, but as a continuous process, each universe passing conditions forward into the next in ways we barely understand. And then the thought turns inward. If universes can pass on their laws, could they pass on their patterns? Could the swirl of galaxies in one cosmos echo faintly in the next, as if the new universe carries a soft genetic memory of the one before it? Not images, not information, but tendencies, structures, symmetries, the kind of deep patterns that shape how stars ignite, how atoms bind, how dimensions unfold. You feel that question open like a door, and beyond it, another. If a new universe is born, would it have time as we know it? Or would time itself be reconstructed, redefined, reimagined from whatever survives the crossing? Quantum gravity theories hint that at the moment of maximum density, time might not behave like a river at all. It could behave like a loop, a shimmer, a reversible pulse. Some models suggest the universe's collapse doesn't end in a singularity, but reaches a minimum volume, a smallest possible size. And at that limit, gravity turns repulsive, pushing outward and birthing expansion once more. You picture it like a soft rebound, not a violent explosion, but a gentle swelling of space-time, as though the universe has exhaled after holding its breath across the entire span of existence. If that is true, then death is not the opposite of beginning. Death is the bridge. And you drift with that thought, moving further into the story of what could happen far beyond the reach of stars, beyond the long fade of matter, into the deep twilight of cosmic time. A new question glows in the quiet around you. If a universe can bounce, could consciousness, this strange awareness you feel now, somehow be part of those cycles? Not your memories, not your identity, but the capacity for the universe to generate observers at all. Could that be something the cosmos carries forward like a seed? You don't need the answer. You only float in the possibility. The universe ends. The universe begins. And somewhere between those two lies a mysterious threshold where physics blurs into something more fluid, more ambiguous, more alive. You drift deeper into the question, letting it expand like a quiet ripple through your thoughts. If a universe can die and another can begin, what machinery of reality performs that transformation? Who first understood that space-time itself might have rhythms? And what clues have been left for you in the equations of the cosmos? Your awareness settles on the work of the physicists who tried to follow these delicate threads. Richard Tolman, in the early 20th century, imagined a universe that could oscillate, expanding and contracting in endless cycles, each one rising from the compression of the last. Decades later, Roger Penrose proposed that the infinitely distant future of one universe could be conformally transformed into the beginning of the next, a theory he called conformal cyclic cosmology. Not a rebound driven by gravity, but a mathematical smoothing of the far future into a new beginning, where the lack of mass and structure allows the universe to forget its scale and become newborn again. You imagine that transformation the way Penrose described it. As the universe thins and grows cold, all particles with mass eventually decay, leaving behind only massless radiation, photons, gravitons, light without matter. In that distant future, scale loses meaning. A trillion light-years and a centimeter become indistinguishable, and in that erasure of scale, the boundary between the dead universe and the next Big Bang becomes soft enough to blur. If that view is true, then the death of our universe does not ignite a new Big Bang violently. It dissolves into one gently. Another path opens as you drift through these ideas. Some researchers working in loop quantum gravity, like Abhay Ashtekar and Martin Bojewald, explored the idea that space-time is not infinitely divisible. Instead, it is granular, woven from discrete quanta of area and volume. In their models, when the universe tries to collapse into a singularity, it reaches a minimum size, not zero, but a smallest possible volume allowed by quantum geometry. At that limit, something remarkable happens. Gravity reverses its role. Instead of pulling inward, it pushes outward, creating expansion from contraction, a big bang from a big crunch. You can almost feel that moment, that quantum rebound, like a soft pivot in reality where what once pulled now releases. It is not destruction, it is transition, a breath turning from inhale to exhale. And still another idea drifts into view, growing from the work of André Linde and Alan Guth, pioneers of inflationary cosmology. In their framework, our universe might be one bubble among many, each formed from quantum fields undergoing brief, explosive inflation. The remarkable part is that inflation might be eternal, even if individual universes are not. While one universe expands, cools, and fades toward heat death, the inflationary field beyond it may birth others. An endless sea of cosmic bubbles, each beginning with a big bang of its own. In that picture, the death of our universe does not cause another big bang, but the universe is constantly giving birth to new ones anyway. The cosmos is not a single history. It is an ongoing process of emergence. A quiet question rises in you. If universes emerge endlessly from deeper fields, do they share anything? Or are they isolated islands in a sea too deep to fathom? Some theories whisper that they could be connected in subtle ways. Patterns in the cosmic microwave background might hint at collisions with other universes. Faint circles, temperature anomalies, echoes from beyond our horizon. Most evidence so far is inconclusive, yet the idea lingers that perhaps our universe has already brushed against others, the way drifting soap bubbles might touch and distort each other's walls before drifting apart again. Your awareness sinks deeper into the long future. A time when the last black hole evaporates into a sigh of Hawking radiation, releasing its stored information in a faint shimmer of photons. a time when particles decay or drift apart so far they may as well be alone forever. A time when the temperature of the universe approaches absolute zero, but never quite reaches it. A faint hum of existence stretched thin across a vast, dark expanse. What then? Does the quiet emptiness wait for a quantum fluctuation large enough to seed a new Big Bang? Is the birth of a universe a rare event, or is it woven into the vacuum itself, always simmering with potential? You drift with that question through the space of possibilities, and another thought settles beside it with gentle gravity. If the cosmos is capable of birthing universes, then perhaps the silence after its own death is not truly silence at all. Perhaps it is a womb, a place where new fields, new energies, new geometries take shape in ways your current physics can barely describe. You sense that you are approaching a deeper layer, a place where ideas from string theory, quantum cosmology, and thermodynamics meet in a single delicate balance. The horizon where endings and beginnings become the same phenomenon seen from different sides. A quiet sense of falling settles around you, not downward, but inward, as though you are drifting deeper into the architecture of the cosmos itself. The further you move, the more the boundary between beginning and ending softens, revealing places where the equations of physics fold into shapes that feel almost alive. You find yourself wondering what it truly means for time to move forward or backward, or to dissolve altogether at the edge of a cosmic cycle. If the universe can end in darkness, yet somehow bloom into brilliance again, what becomes of the arrow of time in that transition? Does it break? Does it reverse? Or does it quietly reshape itself into something new, something unfamiliar but inevitable? The work of Stephen Hawking and James Hartley appears here, their no-boundary proposal suggesting that the Big Bang was not a singular edge, but a smooth curvature of space-time, like the rounded tip of a sphere. In their mathematics, the universe didn't begin with a hard boundary or a sharp creation event. Instead, time gradually emerged from a state that had no clear distinction between past and future. Like dawn rising from the night without a single moment you can point to and say, yes, this is where it began. If the universe could arrive in that way, could it also depart in the same soft manner? Could its death taper into a state beyond time, and from that quiet geometry, a new era unfold without rupture? The question carries you into the ideas of Lee Smolin, who imagined that universes might reproduce through black holes. In his model of cosmological natural selection, each black hole becomes a seed for a new universe, with its own physical constants and laws shaped by the conditions of its parent. Not a multiverse of pure randomness, but one shaped by something like evolution across unimaginably vast cycles. You picture the final age of our cosmos, long after its galaxies have dimmed, where the remaining black holes stand as the last glowing embers in an ocean of cold darkness. Inside each one, gravity compresses matter to densities beyond imagination. Perhaps, in their hidden interiors, a new space-time inflates, separate from our own, carrying forward the information of our universe in ways deeply encoded and impossible to retrieve. A different possibility draws closer, one explored by Paul Steinhardt and Neil Turok in their ekpyrotic and cyclic universe model. Here, the Big Bang is not the birth of everything but the result of two higher-dimensional brains colliding in a larger cosmic arena. Each collision produces a burst of energy that becomes the hot, dense beginning of a universe like ours. After trillions upon trillions of years, as the universe fades and expands, the brains move apart, only to drift together again in the distant future. The next collision becomes the next Big Bang, not as a rebound from collapse, but as a rhythmic meeting of structures beyond our dimensional perception. It feels like listening to a slow, ancient heartbeat that has been pulsing long before stars formed and will continue long after the last photons fade. These ideas settle around you like constellations, each one a different map of what might lie beyond the horizon of cosmic death. And within them, another question begins to glow, subtle but persistent. If the universe is capable of cycling, bouncing, budding, or colliding into new births, what happens to the information carried within it? Does everything we experience vanish without trace? Or does the universe protect its memories the way quantum mechanics seems determined to preserve information, even in places as extreme as black holes? You drift toward the edge of that thought, to the line of research led by physicists like Juan Maldacena, who explored how holographic principles might encode information on cosmic horizons. In this vision, the universe acts like a vast projection, storing its details on surfaces rather than volumes. If that holographic encoding remains even near the end of time, then perhaps the blueprint of the universe survives long enough to seed the next. Not consciously, not deliberately, but woven into the structure of space-time in a way that lets patterns propagate from one cycle to another. The swirl of galaxies, the clustering of matter, even the values of the constants that shape chemistry and life. These could all be part of the deep inheritance of cosmic evolution. And yet, another thread pulls at you, quieter and more elusive. What if time itself is not linear across these transformations? What if the end of the universe does not lie in our future in any conventional sense, and the next Big Bang is not in some distant tomorrow, but connected to us through a geometry that twists time into a loop? Some solutions to Einstein's field equations suggest that what we call the beginning of time could be adjoining what we call the end, not separated by distance but by curvature. In that sense, the universe could be a self-contained story, its death feeding its birth feeding its death, not in cycles stretched across eternity, but in a single continuous structure without external edges. A finite cosmos without boundaries, looping not through repetition but through seamless connection. You drift through these possibilities like a traveler moving through overlapping dreamscapes. Each theory is a lens, each lens a new view of what an ending might truly be. The universe cools, it fades, it dissipates into thin, quiet emptiness. But the laws that govern that fading also allow for renewal, for transitions, for emergence out of stillness. And the more you contemplate this, the more you sense a deeper truth forming beneath the surface. That reality might not permit absolute nothingness. Even in its quietest state, the vacuum is restless. Fields shimmer with potential, and the seeds of creation remain embedded in the silence. You drift further, deeper still, into a realm where the final photons of this universe stretch across space like threads of ancient light. Between them lies a darkness so vast it begins to feel warm in its stillness. You imagine the final horizon of time pulling away, leaving behind a cosmos without stars, without heat, without motion. And in that serenity, you feel the subtle vibration of quantum fields that never truly vanish, the quiet fluctuations that might one day swell into a new burst of space-time. It is here, in the depths of the universe's long fade, that the question becomes almost intimate. When everything falls silent, what remains capable of creating a new beginning? Is it gravity collapsing space-time to its limits? Is it the decay of the vacuum unlocking new energies? Is it the touch of dimensions beyond our sight? Or is it something simpler and more fundamental? The tendency of the cosmos to transform rather than end. You drift there, suspended in the thought that death and birth may not be opposites at all, but two sides of the same motion woven into the foundation of existence. Far ahead in the dark future of the cosmos, a different image begins to take shape, one that does not rely on motion or drifting at all. Instead, it stands still in front of you, like a giant sculpture of time frozen at the moment before transformation. The universe has expanded into near emptiness. Temperatures hover just above absolute zero. The last traces of starlight have long since stretched into wavelengths larger than galaxies. What once was vibrant and bright now resembles a single breath held for an impossible span of ages. In that stillness, a question quietly sharpens. What mechanism could possibly ignite a new beginning from something so quiet, so diluted, so faint? The thinking turns to black holes, not as monsters of destruction, but as engines of deep physics. They evaporate through Hawking radiation, releasing their stored information in the faintest whisper of photons. For physicists like Sabine Hossenfelder and others studying quantum gravity, this evaporation isn't just a slow fade. It is a potential gateway to regimes where space-time abandons classical rules. At the final moments of evaporation, the energies involved might approach Planck scales, the domain where quantum effects of gravity become unavoidable. Could such conditions mimic the dense, hot environment of a newborn universe? Could the last, dying black hole, in the final instant of its life, seed the first moment of another? The possibility is neither confirmed nor dismissed. It lies in the space where theory stretches against the edge of what equations can reliably describe. Another idea comes from the strange world of vacuum energy. Modern physics knows that empty space isn't truly empty. Even in the coldest darkness, quantum fields continually ripple with tiny fluctuations. These fluctuations sometimes create virtual particles, sometimes annihilate them, and occasionally, if conditions align, produce something far more dramatic. In the deep future, where the universe approaches thermal silence, the vacuum may still possess a latent instability. If the Higgs field, for instance, sits in a metastable state as some interpretations of particle physics suggest, then a rare quantum event could tip it into a lower energy configuration. That transition would release immense energy, creating a bubble of new physics that expands at the speed of light. Inside the bubble, conditions resemble a Big Bang, hot, dense, energetic, ready to evolve. Not a cosmic rebound, not a collapse, a phase change. It raises another question that settles with a quiet gravity. If a new universe emerges through such a transition, does it occur after ours in any meaningful sense? Or does it exist as an entirely separate realm, branching from a moment unrelated to our cosmic timeline? Time. Inside, the bubble begins anew. Its expansion is independent. Its laws may differ. To us, it would be as though a new sheet of reality had been placed adjacent to our own, without ever touching. The thought leads naturally into the mathematical realms opened by string theory. In that framework, space-time is not merely the three dimensions you see and the one you feel as time. Additional dimensions curl and compactify around every point, shaping the behavior of particles and fields. The death of a universe could involve the rearrangement of these hidden dimensions, a collapse of one geometric configuration into another, and that rearrangement could unleash energy in a form indistinguishable from a Big Bang. Edward Witten and other pioneers in the field considered scenarios where transitions between different vacuum states, different configurations of strings and branes, could generate new universes. In this picture, the end of a universe is a kind of topological shift, a reconfiguration of the deep structure of reality that births a new phase of existence. Another idea rises from the work of Penrose, a vision where the far future of the cosmos becomes so dilute and so dominated by massless particles that the concept of scale disappears entirely. Without scale, the infinite future becomes mathematically transformable into a finite beginning. The universe's death becomes indistinguishable from its birth, a smooth handoff between aeons, each one beginning where the last one faded into the loss of structure. In this view, information from our universe could be subtly imprinted on the next, not in memories, not in images, but in structural patterns. A faint signature embedded into the radiation that survives across aeons. The idea suggests that the universe might not simply die. It might surrender its structure in a way that leaves behind a trace, a signature that seeds the next cycle. This brings forward another question that feels both enormous and intimate. Does the universe evolve across cycles? Could laws of nature change slowly, subtly, as universes follow each other in long sequences? Smoline's evolutionary cosmology considers this. Steinhardt's cyclic models touch it. Even inflationary cosmology, in its eternal form, hints at a landscape of universes where different constants arise naturally. It leads to a vision where universes are not static artifacts, but participants in a larger unfolding, exploring different combinations of laws the way biological systems explore forms. In this view, the death of one universe may be part of a process that shapes the conditions of the next, a cosmic inheritance not of matter, but of possibility. Here, in this thought space, the end of everything no longer feels like a void. It feels like a hinge, a threshold where one form of physics gives way to another. The Big Bang ceases to be the beginning of all beginnings and becomes the latest chapter in a lineage far older and far broader than what human senses can perceive. And so the question settles into its most refined shape. If our universe dies, does it end its story, or does it simply release the conditions for the next one to arise? In the far reaches of cosmic time, when the universe has aged beyond the span of stars, an even deeper question begins to take form. Where do the laws of physics themselves come from? And are they stable across the death and rebirth of universmic cycles? If each Big Bang marks a new unfolding, what determines the rules that shape that unfolding? The gravitational constant, the strengths of forces, the masses of particles. These aren't arbitrary. They sculpt the very possibility of atoms, molecules, stars, and life. If a new universe emerges from the remnants of an older one, do these constants reset, or do they carry some imprint of the cosmos that came before? This question touches the edges of modern cosmological research. It draws from the landscape of string theory, where the vacuum isn't a single configuration, but one possibility among perhaps 500 different states. In that vast landscape, universes can emerge with different parameters depending on how dimensions are curled, how branes align, and how fields stabilize. The death of a universe could trigger a shift from one vacuum to another, not unlike the way the early universe underwent symmetry-breaking events that shaped the forces of nature. If the collapse or decay of our cosmos selects a particular vacuum state, then the next universe could inherit a set of laws shaped by conditions at the transition. A thought rises. Perhaps the conditions at the universe's death aren't the end of the story. They're the final constraint that determines the form of what comes next. The idea grows more intricate when you consider the concept of cosmic entropy. Entropy, the measure of disorder, increases relentlessly as the universe ages. Over unimaginable timescales, entropy dominates everything, driving the universe toward an even distribution of energy. But when a universe collapses, or transitions to a new vacuum, what happens to its entropy? Does it vanish? Is it encoded? Is it transformed? Can a new universe begin with low entropy if the previous universe ended with high entropy? Penrose wrestled with this paradox deeply. His conformal cyclic cosmology addresses it by proposing that when the universe becomes dominated entirely by massless particles in the far, far future, when all black holes have evaporated, when all matter has decayed, entropy becomes impossible to define. Without mass, without structure, without clocks that can measure change, the universe loses the very concept of disorder. Scale no longer exists, and in the absence of scale, the high entropy state of the old universe can be reinterpreted as the low entropy beginning of the next. A conceptual bridge where complexity dissolves into pure geometry, and from that geometry, a new era begins. Another line of research asks a different question. What if new universes form not from the entirety of a dying cosmos, but from specific regions within it? In theories of eternal inflation, pioneered by Linday and Guth, quantum fluctuations in the inflaton field create bubble universes that expand into their own cosmological domains, each with its own Big Bang. These bubbles do not require the parent universe to die. They form spontaneously in a broader inflationary space, like sparks in a dark sea. In this scenario, the death of our universe is irrelevant to the birth of another. The cosmos is a garden where universes continually sprout regardless of what happens to any individual one. Yet that view raises its own profound question. If universes arise independently, then what is the purpose of cosmic death? Is an ending simply a quiet fade into irrelevance, or does it shape the deeper fabric of the multiverse? Could the death of a universe influence the larger field in which universes emerge, altering the probabilities of new births, the structures of dimensions, or the energies available for creation? Here, you encounter an idea studied by physicists like Raphael Bousso, who explored the holographic structure of de Sitter space. In universes dominated by dark energy, like the one ours is becoming, the existence of a cosmic horizon limits the amount of information accessible within any region. If the universe dies in this state, its final imprint might be stored on this horizon, encoded in a way that shapes the vacuum energy of the broader multiverse. The death of a universe, in this perspective, leaves a kind of holographic shadow that may influence how new universes emerge. The question deepens. Could the final state of our cosmos, its geometry and information content, become part of the initial conditions for a new one? Even if the transfer is subtle, perhaps only statistical, it would mean that universes are not isolated stories, but chapters in an ongoing evolution. As you move through these possibilities, you begin to sense the strange unity at the heart of all these ideas. Whether through collapse, transition, vacuum decay, quantum fluctuation, or brain collision, many theories agree on one thing: the universe is not static. It does not exist as a single, isolated event. It is part of a larger process, one that cannot end in the absolute sense, because the very fabric of reality seems predisposed toward transformation. The end of all stars does not mean the end of all beginnings. The fading of galaxies does not mean the cessation of creation. Even the silence of heat death contains the seeds of emergence. A final question forms, subtle and immense. If the universe is a part of a continuous chain, if its death is the doorway through which new universes appear, then what lies beyond the chain itself? Is there a deeper structure, a metacosmic order guiding these transitions? Or is the multiverse itself the fundamental reality, without beginning or end? And if there is no first universe and no last, then the question shifts again. Perhaps the cosmos is not a story with a beginning and an ending, but an eternal conversation between existence and possibility. In that imagined silence where universes age, dissolve, and give rise to new ones, another idea begins to take shape. Not from imagination, but from the questions real physicists wrestle with when equations grow too vast for certainty. It is the question of whether time itself might be an emergent property, something that appears only under specific conditions and disappears when those conditions vanish. If time can fade, then what becomes of a universe when time no longer flows? And if a new universe forms, does time reappear as a fresh dimension, shaped by the first motions of energy and expansion? This thought leads directly to the work of Carlo Rovelli, who has spent decades exploring the concept that time is not fundamental but relational. In some formulations of quantum gravity, the universe near the moment of a Big Bang or Big Crunch loses its familiar ordering of before and after. Events do not line up in sequence. Instead, the properties of the universe define each other without a background timeline. If the death of a universe leads to conditions where time dissipates, then its rebirth might involve the reemergence of time as patterns reestablish themselves. Expansion gives direction. Cooling gives sequence. Structure creates the arrow. In this sense, the Big Bang of a new universe is not just an explosion of matter, but the ignition of time itself. Another question rises naturally. Could any trace of our universe survive such an extinction and reformation? Black hole evaporation suggests that information cannot be destroyed. Holographic principles insist that physical details can be encoded in the geometry of horizons. If a new universe forms through a bounce or transition, some of these encoded patterns might influence the initial conditions. Not in the form of memories or recognizable structures, but as subtle fingerprints. Differences in density fluctuations, slight variations in the strengths of forces, or faint directional preferences in the cosmic background radiation of the next cosmos. Research teams studying the earliest light of our universe have occasionally reported anomalies, unusual alignments or temperature distributions that some have speculated might hint at events from before our own Big Bang. While controversial and far from confirmed, these observations invite a profound possibility that the universe may carry whispers of its ancestry. The image that follows is not poetic. It is mathematical. Imagine a collapsing universe approaching a point of extreme density. Ordinary space-time breaks down. Quantum geometry takes over. Fluctuations become dominant. In loop quantum cosmology, the equations describing this moment replace the singularity with a minimum volume, a turning point. On one side lies collapse. On the other lies expansion. This transition does not erase everything. It reshapes it. The quantum state of the universe before the bounce influences the quantum state after. What appears as a Big Bang is connected, smoothly through mathematics, to what lies beyond it. Yet not all endings require collapse. In a universe destined for heat death, conditions become so sparse that quantum events gain an outsized influence on large scales. A tiny fluctuation in a vacuum field could, with the right configuration, give rise to rapid inflation. Inflation smooths space, flattens curvature, and erases detail. But the initial trigger, the spark, need not be random. It could be shaped by the parameters of the dying universe's vacuum. Even the value of dark energy could imprint a constraint on the next cosmic cycle. This leads to the unsettling but beautiful idea that universes might evolve across generations, not biologically, but physically. Constants that promote the formation of black holes could become more common. Configurations that lead to long-lived stars might be statistically favored. Over countless cycles, universes might drift toward conditions that maximize complexity. In that sense, the death of one universe becomes part of the natural selection process of cosmic architecture. Another thought takes hold. If cycles or branches of universes are part of a larger structure, is there a medium that holds them together? In quantum cosmology, the wave function of the universe does not describe a single outcome. It describes a spectrum of possible universes evolving simultaneously in a higher dimensional configuration space. Our universe is one path through that landscape. Another universe could follow a different path. The death of our path might influence the broader wave function, altering the landscape's contours and guiding future universes along certain trajectories. Here, endings and beginnings dissolve into something more intricate. A universe does not simply stop. It changes the probability landscape for what comes next. And yet, beneath all these possibilities, another question quietly sharpens. What is the engine driving this endless movement between forms? Energy decays, structures break, particles fall apart. But the underlying fields remain. The vacuum never fully empties. Even at maximum entropy, fluctuations persist. The universe retains a kind of potential, not kinetic, not thermal, but foundational. A restlessness built into the quantum nature of reality itself. This restlessness might be the true origin of cosmic rebirth. A universe can die, but the fields that allowed it to exist never stop vibrating. They are not born with the universe, nor do they perish with it. They are the deeper fabric from which universes arise. This perspective brings forward one final idea. Perhaps the death of a universe does not cause a new Big Bang in the causal sense. Perhaps it simply clears the stage, removes structure, dissolves complexity, returns the cosmic field to a state where it can once again express its potential by forming a new universe. Not an explosion triggered by death, but a new beginning made possible by silence. In this way, the end of a universe is not a mechanism. It is a condition, a necessary clearing that allows the next expression of space-time to unfold. In the quiet after-stars era, where matter has thinned to almost nothing, a different picture begins to form. One where the universe resembles a vast, cooling laboratory. Every remnant particle, every fading photon, every last gravitational wave is still governed by rules that never lose their authority. even as the cosmos grows empty. And here, in this near-silent expanse, a thought presses forward. What if the most important part of creating a new universe is not energy, but structure? What if emptiness must reach a particular state before anything new can ignite? Physicists studying quantum fields often describe the vacuum as having multiple possible configurations, like a landscape of valleys and ridges. The state our universe currently occupies could be only one valley among many. The death of the universe, its long descent toward cold simplicity, might bring it closer to a boundary where a different valley becomes accessible. A rare fluctuation could nudge the vacuum into that new configuration, releasing tremendous energy. That transition would resemble the beginning of a cosmos, a tiny bubble of new space-time racing outward, shaping its own geometry and physical laws. A curious detail emerges here. If the vacuum of the dying universe sits just slightly higher in energy than a deeper, more stable vacuum, then the entire cosmos could remain precariously balanced. A shift to the lower energy state wouldn't merely add energy to the universe, it would redefine space-time. The old structure would vanish locally, replaced by the expanding bubble of new physics. To any observer caught within it, that bubble would look like a newborn universe. It raises a strange possibility. The next Big Bang might already be encoded in the very fields that surround us now, waiting for the cosmic environment to reach a quiet enough condition for the transition to begin. A different path takes shape when contemplating gravity itself. As the universe ages, its gravitational geometry becomes increasingly simple. Galaxies evaporate from one another's horizons. Black holes diminish. Large-scale curvature flattens. The entire cosmos approaches a nearly featureless state. In general relativity, such simplicity often hints at symmetry, and symmetry can be a seed of change. Paul Steinhardt's cyclic models take advantage of this idea, that when the universe enters a period of vast, calm expansion, hidden dimensions might begin to shift, like tectonic plates moving beneath an ocean. Those shifts release energy in sudden, powerful bursts, igniting new cosmological epochs. Imagine that. A dark, cold universe quietly rearranging itself in dimensions you cannot sense until a geometric snap sends shock waves through the fabric of existence, birthing a new era with new properties. Another question rises from this. If universes can begin through transitions and rearrangements rather than collapses, then what determines their diversity? Why does our universe have 3 large spatial dimensions and not 5? Why does gravity stretch across cosmic distances while the strong force clings tightly to atomic nuclei? Research by string theorists suggests that the shape of compact extra dimensions dictates these properties. When a universe dies and the vacuum shifts, those shapes could change. A curled dimension might unfurl slightly. A twisted loop might tighten. These minute transformations could result in a universe with entirely new constants: lighter particles, stronger forces, shorter-lived stars. In that sense, the death of a universe becomes a kind of reset of the cosmic blueprint. But an even more provocative idea lies beneath. What if the parameters of a universe are not random, but influenced by what came before? If certain vacuum states are easier to reach after long periods of expansion, then universes might gradually migrate toward states with particular characteristics. Over immense cycles, this could create something like an evolutionary trend across generations of universes. Not purpose-driven, but statistically favored. a gradual shaping of what kinds of cosmos can exist. The thought is subtle but profound. Maybe universes collect tendencies the way rivers carve paths. Not memories, not history, just a growing preference for certain forms. That leads to another puzzle. If universes arise from earlier ones, could some of the most puzzling features of our cosmos be relics of a previous generation? The near-perfect uniformity of the cosmic microwave background, the fine balance between expansion and gravity, the precise values of the fundamental constants. These might not be coincidences at all, but the stabilized outcomes of a long lineage of cosmic cycles. Yet no single theory answers this comfortably. Instead, they all circle a central theme. The end of a universe does not resemble a wall. It resembles a threshold, a transformation point where the familiar rules lose their grip and deeper ones take over. Whether through collapse, vacuum transition, dimensional shifts, or quantum birth, the universe seems to protect one truth above all. Endings cannot remain endings forever. There is always a mechanism, somewhere in the mathematics, that nudges reality toward renewal. And this realization opens the door to a final, sharper question. If the cosmos is capable of renewing itself, what determines the moment when silence becomes creation? Is it driven by decay reaching its limit? By quantum fields settling into rare alignments? By geometry twisting itself into a new configuration? Or is it something even simpler, an inevitability built into the very nature of existence, that the universe cannot remain still? In the deep quiet at the end of cosmic time, the universe may find itself balanced at an exquisite point, a state so simple that even the smallest fluctuation could transform it. And from that smallest fluctuation, a new era might ignite, as natural and effortless as a spark catching fire in the dark. In the darkness where nearly all structure has fallen away, the universe resembles a vast, chilled canvas with almost nothing painted on it. But the lack of structure does not mean the lack of possibility. It means the opposite. It means the rules that once constrained the cosmos, dense matter, bright radiation, complex interactions, have thinned enough for deeper behaviors to emerge. The universe becomes transparent to its own foundations. A thought begins to form here, subtle but powerful. Perhaps creation is simplest when the cosmos is emptiest. This idea emerges from quantum cosmology research, where physicists explore how vacuum states behave under extreme conditions. When the density of matter falls low enough and the temperature drops near zero, certain unlikely processes become more plausible. Rare fluctuations, normally drowned out by the activity of a younger universe, rise into significance. One such fluctuation could warp spacetime in a precise configuration. If it meets the criteria for inflation, it could ignite a new expansion phase, a fresh cosmos blooming from almost nothing. But there is an important nuance. Inflation does not merely start because energy is present. It begins because space itself is positioned in a certain state, a state where its geometry permits rapid, exponential growth. This raises a new question. Does the death of a universe prepare space for that state? Alan Guth once remarked that inflation only needs a spark to begin, but the spark must fall into the right environment. The long cooling of a universe, its descent toward simplicity, might be the cosmic equivalent of clearing dry ground. The vacuum becomes smooth, stable, nearly uniform. It holds almost no structure to resist a change. A small fluctuation, which in a warm, active universe would collapse, could instead stretch and expand. The emptier the cosmos becomes, the more sensitive it is to these triggers. This perspective casts the end of the universe not as decay, but as preparation. Another avenue of thought appears when considering the underlying mathematical language of physics. In general relativity, space-time is dynamic. It responds to energy, mass, motion. But in certain quantum gravity formulations, space-time does not simply respond. It originates from deeper relations. Some interpretations suggest that when these relations reach maximum simplicity, they undergo transitions much like phase changes in materials. Ice melts, metals magnetize, crystals form. Perhaps space-time undergoes its own phase changes when the universe reaches extreme stillness. Picture a cosmos stretched thin, cooled nearly to nothing, with its fields in a delicate balance. A slight reconfiguration, so slight you could not call it motion, could shift the vacuum into a new arrangement. And that arrangement might be unstable in a productive way, leading to runaway expansion. The Big Bang, in this sense, becomes the natural result of a phase shift in the fabric of reality itself. This brings forward another powerful idea. Maybe the universe does not need energy to begin. Maybe it needs symmetry. A universe filled with stars and galaxies is asymmetric, messy, heavy, uneven. But a universe drained of heat, matter, and curvature becomes closer to perfect symmetry. In physics, perfect symmetry is rarely stable. It invites transitions. When the symmetry breaks, new structures appear. Forces separate. Dimensions settle. The cosmos gains direction. It gains texture. It gains time. So, as the universe dies, it moves closer to the conditions where a symmetry-breaking event could act as the seed for a new creation. This casts the cosmic end in a different light. Not a final breath, but a return to a pristine state so finely balanced that it becomes fertile ground for transformation. Every evaporated black hole, every decayed particle, every faded photon contributes to that long approach toward near featureless simplicity. And yet, the idea that symmetry drives new beginnings asks another question. What role do dimensional changes play? In string theory and brain cosmology, dimensions are not fixed. They can stretch, compactify, or twist under certain conditions. If a universe reaches a stage where energy densities are nearly zero, the compact dimensions might shift in size or topology. A tiny adjustment could create tension between branes or alter the geometry of extra dimensions. That tension could release energy in a burst that resembles a new cosmological epoch. In this picture, the universe does not restart because it dies. It restarts because its underlying dimensional structure becomes unstable in the calm. Another layer becomes visible when considering the fate of dark energy. If dark energy is truly constant, the universe will drift into an eternal expansion. But if dark energy evolves slowly across vast timescales, something current observations can't yet rule out, it could eventually decline. A universe once dominated by expansion might return to a state governed by gravity. If gravity regains its influence, contraction begins. And contraction brings rising temperature, increasing density, and a tightening of space-time. As contraction accelerates, everything simplifies again. Galaxies merge. Matter compresses. Radiation intensifies. The cosmos approaches conditions reminiscent of the early universe. And if quantum gravity prevents a true singularity, a bounce becomes possible. The contracting universe reaches a smallest size, tiny but non-zero, and then rebounds into a new expansion phase. In this scenario, the death of the universe is not the stillness of heat, death, but the tension of collapse. And the next Big Bang is not a quantum fluctuation, but the natural rebound from a cosmic minimum. Yet even in these vastly different models, a pattern emerges. The universe moves toward a state that resets its conditions. Whether through expansion into emptiness or collapse into density, the cosmos seems drawn toward points of transition where the next era can ignite. From here, a final thought gathers. Every star, every force, every particle arises from the interplay of rules that define our universe. And those rules might be transient. They might belong only to this cycle, this vacuum state, this dimensional arrangement. A new universe might not just begin in a different environment. It might begin with different laws entirely. If that is true, then the death of our universe could be the moment when those deeper rules become free to rearrange themselves. Not chaos, but simplicity so extreme that the structure beneath physics is allowed to reconfigure. And from that reconfiguration, a new cosmos may rise, not as a replica of ours, but as a new expression of what reality can be. Across unimaginable ages, as the cosmos sinks further into its quiet state, the question becomes sharper. What hidden processes still operate when nearly everything else has fallen silent? Even at the brink of cosmic emptiness, the laws of physics do not stop. They only shift into domains that rarely appear while stars still burn. And within these domains, new possibilities appear. Possibilities that only reveal themselves when the universe is old enough, sparse enough, and calm enough for subtle effects to dominate. One of those effects is quantum tunneling on a cosmic scale. Normally, tunneling is a microscopic phenomenon. Particles slipping through barriers they lack the energy to cross. But in some models of quantum gravity, entire regions of spacetime can tunnel into new configurations. The vacuum itself can tunnel. A dying universe, lightless, cold, nearly flat, may be closer to the edge of such a transition than a young and energetic one. A tiny patch of spacetime might suddenly find itself in a state with slightly different energy, slightly altered geometry. And from that single change, the entire region could inflate, becoming a universe with its own version of space and time. If this process occurs, then the silence of an aged universe is not a dead end. It is the delicate pause before a rare transformation. To understand why this matters, consider an unexpected insight from thermodynamics. Not everything in physics becomes less interesting as entropy rises. While most classical structures decay, quantum effects often grow more influential when things cool down. In the late universe, with almost all energy spent, quantum fields remain the only active players. They ripple softly across an immense void. Their fluctuations, once irrelevant noise, become the only sparks left. And a single spark in the right configuration might create a region where a spacetime curves violently outward. From the inside, that violent curvature appears as a brilliant hot origin, a Big Bang. Another route appears when considering the geometry of space under extreme expansion. As dark energy continues pushing galaxies apart, the cosmos becomes dominated by the horizon beyond which nothing can be seen. In this horizon-dominated regime, spacetime begins to resemble de Sitter space. Some researchers, like Leonard Susskind and others exploring holography, point out that de Sitter space is inherently unstable. If the universe truly approaches this form, it may contain seeds of its own breakdown. Its horizon could be the surface upon which the next universe gestates. The information of this cosmos stretched thin across a sphere that slowly morphs into the boundary of a new one. the horizon becomes a chrysalis. This concept shifts the focus from the interior of the universe to its outermost boundary, where space-time thins so much that its rules take on new forms. If information is encoded there, and the horizon slowly loses its meaning as the universe cools, the transition to a new Big Bang could begin at the very edge of reality, where geometry becomes fluid and undefined. A different possibility arises from the mathematics of higher dimensional models. If our universe exists on a brane floating within a larger dimensional structure, then its eventual decay might loosen the constraints that bind it. As the brane relaxes, it could collide with a neighboring brane, or slip into a different configuration. Such an event releases unimaginable energy, not as a violent fragmentation of old matter, but as the birth of new spacetime. The universe would not break, it would reconfigure. The Big Bang would be the aftershock of geometric motion in dimensions you never perceive. In this picture, the universe's end is akin to a shift in tension, like the final relaxation of a stretched membrane that snaps into a new position, reshaping everything. This raises another question, subtle but profound. What determines the moment when the universe becomes ready to change? Is it a threshold of curvature, a specific energy level, a point of maximum symmetry? Or is it statistical, the result of improbable fluctuations eventually becoming guaranteed over infinite time? Some physicists argue that a true heat death, an eternity of stillness and maximum entropy, is unstable. Not because anything remains to decay or collapse, but because perfect uniformity is naturally vulnerable. A fluctuation, no matter how unlikely, will eventually appear. Over truly limitless time, even the rarest event becomes inevitable. And if even one fluctuation triggers inflation, that region becomes the birthplace of a new universe. This perspective paints the cosmos not as a single vast narrative, but as a sea of potentials in which renewal is almost guaranteed by the sheer weight of infinite time. Death is only a long pause between awakenings, yet the nature of that awakening remains mysterious. Does a new universe emerge with entirely new laws, or do vestiges of its predecessor shape its initial conditions? The idea that information cannot be destroyed suggests that something, some encoded structure, survives even across extreme transformations. That structure might be faint, like a signature woven into the initial quantum state of a newborn cosmos. It might affect symmetry breaking, or the amplitude of primordial fluctuations, or the behavior of its earliest fields. If that is true, then the next universe carries a quiet inheritance. Not memories, not galaxies, but tendencies, patterns, preferences for certain forms of physics over others. The cosmos then resembles a lineage not of copies, but of descendants. Each universe different. Each universe shaped faintly by the death that preceded it. And so the idea of cosmic death shifts again. It is not a final extinguishing of everything, nor a cliff at the edge of existence. It is a subtle thinning of complexity until the rules beneath reality become free to change shape. Like embers, cooling until the deeper grain of the wood reveals itself, allowing a new fire to begin from the faintest spark. The final image is stark, yet strangely comforting. A universe so old it has forgotten the sound of stars, resting in a silence so complete that even the vacuum hums with anticipation. Nothing moves quickly, nothing shines. But hidden in that stillness are the deepest mechanics of nature, waiting for the precise moment when a rare fluctuation, A shift in geometry or a change in dimensional structure sets off something astonishing. Not destruction, not repetition, the quiet ignition of a new reality. In the dimmest ages of the cosmos, where the last traces of starlight have stretched into wavelengths broader than entire galaxies, the universe becomes a place so cold and sparse that its very silence feels ancient. Nothing dramatic remains. No supernovae tearing through the void. No galaxies colliding in slow, luminous spirals. No clusters tugging one another across cosmic filaments. Only a thin mist of particles separated by distances so vast they no longer meaningfully interact. Yet this near-perfect emptiness is not without direction. It moves toward a particular kind of simplicity, one where the universe becomes almost entirely defined by the properties of the vacuum, rather than the matter floating inside it. What emerges here is a landscape governed not by stars or galaxies, but by rules that never fade. The quantum fields that underlie all of existence. These fields never rest. Even when matter vanishes and radiation cools toward nothing, the fields continue to flicker, their fluctuations woven into the very fabric of space-time. That realization draws attention to something essential. When the universe finally reaches its dimmest state, it might not be the mass, or the temperature, or the curvature that matters most. It might be the behavior of the vacuum itself. In the earliest days of cosmology, the vacuum was considered empty, a simple nothingness. But quantum theory revealed it to be a restless medium, full of transient activity that flickers at scales smaller than imagination can comfortably hold. This restless vacuum, even at the end of time, could contain the seeds of a new universe. One fluctuation, if tuned in a way that inflationary energy can amplify, would be enough to create a bubble of new space-time. The possibility that such a bubble could emerge at random becomes more compelling when viewed through the mathematics of eternal inflation. In that framework, once inflation begins, it naturally continues in some regions even as it ends in others. Our universe may be just one pocket where inflation stopped, leaving behind a calm cosmos. But far beyond our horizon, or in eras unfathomably distant, other pockets might ignite. Universes budding like dew forming on an invisible field. And the death of our universe, with its cooling and thinning, might simply increase the likelihood of such a spark occurring within its boundaries. This leads to a new thought. What if the next universe does not arise from everything collapsing inward, but from a single quantum event at the far edges of stillness? Such an event would not resemble an explosion or rebirth in the poetic sense. It would begin quietly, as a tiny domain where the vacuum slips into a different configuration. In milliseconds, that domain would begin inflating faster than the speed of light, not traveling through space, but expanding space itself. It would tear away from the old universe. From the outside, nothing visible would happen. From the inside, a new cosmos would experience its first seconds as a roaring surge of heat and density. To any beings that arise in that distant realm, their Big Bang would appear to be the absolute beginning. Behind them, the shadow of our universe would be unreachable, unobservable, and forgotten by all but the theoretical frameworks that whisper of lineage across cosmic epochs. Yet, to reach this threshold, the universe must approach something extremely rare in physics, near perfect uniformity. Not uniformity in matter, that has long faded, but uniformity in the structure of spacetime itself. Fluctuations that once echoed through the cosmic microwave background eventually dissipate. Gravitational waves stretch into near immobility. The geometry becomes eerily smooth. At that level of smoothness, even tiny quantum variations gain significance. The universe becomes a place where a whisper of energy can reshape the rules entirely. This idea carries echoes of the Hartley-Hawking no-boundary proposal, which suggests that time might behave in strange ways near cosmic extremes. When the universe becomes incredibly simple, time may lose its defining arrow. What remains is a geometry that can transition into another phase without needing a conventional before and after. A dying universe and a newborn one might be two states of a wider geometry, two surfaces on a single structure, connected not by causation but by timelessness. The image this creates is neither a bounce nor a collapse nor a spontaneous popping of reality. It is a transformation across a domain where time becomes irrelevant. One cosmos fades into uniformity. Another arises from that same uniformity, reinterpreted through a different regime of physics. But another theory draws attention in a different direction, one rooted in the notion that black holes themselves may be the engines of cosmic rebirth. Researchers like Lee Smolin have proposed that the interior of a black hole, where classical physics predicts a singularity, might instead become a place where space-time pinches off into a new branch. The extreme compression of matter, once thought to be a terminal point, might ignite a region of fresh expansion. If that expansion grows enough to become its own autonomous space-time, then each black hole in a universe becomes a portal through which new universes are born. Consider this carefully. Every black hole, even the smallest, contains within it a horizon beyond which no information can escape. But what if that horizon is not a prison, but a boundary separating two realms, our universe on one side, a nascent cosmos on the other? Over the lifetime of the universe, trillions of black holes would have formed, each potentially contributing to a cosmic family tree. And when our universe dies, the universes it seeded would continue unaffected, each growing, evolving, developing its own physics. In this scenario, the death of our universe is not a requirement for a new Big Bang. New universes arise while ours still lives. But its eventual end contributes to the selection of traits in its descendants, since universes that produce more black holes yield more offspring. Over incomprehensible cycles, the constants that favor black hole formation might become statistically preferred. This suggests that the conditions of our universe, its particle masses, its force strengths, could reflect the evolutionary pressures of cosmic reproduction. Now consider the opposite perspective, one championed by Penrose. Universes do not form inside black holes, nor do they begin from collapse. Instead, they arise when all structure decays so thoroughly that the cosmos becomes defined only by massless radiation. In this final era, when no clocks exist and no particles define rest, time loses meaning. And without scale or time, the universe's far future becomes mathematically reinterpretable as the beginning of a new one. Not a bounce, not a pop, but an elegant redescription of the same geometric surface. In that interpretation, the death of our universe and the next Big Bang are not separate events. They are adjacent regions of the same cosmological picture. Another framework, known as ekpyrotic cosmology, paints a different portrait. Here, our universe exists on a three-dimensional brane, floating in a higher dimensional space. The death of our universe corresponds to the brane's drifting apart, thinning the cosmos into scarcity. when they approach again, over timescales inconceivable, the collision releases energy that becomes a new Big Bang. A quiet drift in higher dimensions sets the stage, and a sudden geometric contact triggers a fresh beginning. This concept allows the universe to cycle endlessly without requiring a collapse of matter. Instead, the geometry of dimensions themselves conducts the rhythm. Across these theories, the role of cosmic death evolves. It becomes clear that the end of a universe is not a singular concept. It can be a collapse into density, a fade into stillness, a drift into geometric instability, a vacuum waiting for transition, a brain moving toward collision, a horizon evaporating, a black hole giving birth a symmetry preparing to break. And in each scenario, the death is not the final act. It is the precondition for something rare and remarkable. What fascinates physicists most is the growing possibility that the next Big Bang might not simply happen after ours ends, but because the end creates specific conditions. The thinning of matter, the cooling of fields, the approach toward simplicity, the sharpening of symmetry. Each of these could be the quiet scaffold upon which new space-time takes shape. Yet this leads to an even larger question. Does the cosmos follow a kind of grand cycle, or is it a branching network with no single lineage? Does each universe build upon the last, or do they multiply endlessly in all directions? If the universe cycles through collapse and rebound, it is a single thread pulling itself through time. If it buds new universes through quantum fluctuations, it becomes a tree. If every black hole births a new universe, it becomes a forest. If brains collide across higher dimensions, it becomes a tide. If the vacuum shifts into new states, it becomes a sequence of transformations, like matter turning into plasma, then gas, then stars. These images are not metaphors. They are attempts to describe the known mathematics using forms the mind can hold. But the truth is likely stranger. A universe dying could be the loosening of the deepest scaffolding of physics, a dissolving of constraints, a preparation for a phase of reality where new structure can emerge, shaped not only by randomness, but by the inheritance of everything that came before. Somewhere in that vast quiet, a fluctuation will eventually occur, a shift in geometry, a tunneling of the vacuum, a collapse of dimensions, a final horizon evaporating, a brain drawing close, a gravitational bounce at the smallest allowed volume, and from that event, tiny, fragile, invisible in the enormity of the old universe, a new cosmos will blaze into existence with its own sky, its own stars, and its own future. The death of ours becomes the faint, distant prelude to that next dawn. Far beyond the last flicker of starlight, when the universe has become a place defined almost entirely by cold geometry and faint quantum murmurs, the question of how a new beginning emerges becomes more subtle. There is no single event, no dramatic trigger, no cosmic drumbeat announcing the end. Instead, the universe changes character slowly, patiently, shedding complexities until only the deepest structures remain. And those structures, once they reach a certain calmness, begin to behave in ways that were impossible while stars still burned. A remarkable thing happens when a universe grows old. The hierarchy of physical processes inverts. In the early cosmos, everything was driven by high energy, by collisions, by density and temperature. But in the final eras, as energy drains away, the smallest effects begin to rise in significance. A field that once whispered beneath the roar of cosmic activity now becomes one of the only voices left. Space-time itself, stretched smooth across incomprehensible distances, begins to reveal features that were once overshadowed by matter. This is where some theories see the seeds of a new universe forming, not through violence, but through subtle reconfiguration. A vacuum state that has been stable for trillions upon trillions of years might, under the growing simplicity of the cosmos, become susceptible to a rare transition. A shift so delicate it would be invisible to any process we know today. But if such a transition occurs, the energy released in that tiny region could accelerate space at rates that resemble the earliest moments of a Big Bang. A bubble of new space-time would expand, not pushing anything aside, but severing itself cleanly from our fading universe. Inside, time would begin its own story. Another possibility arises when considering the fundamental geometry of the universe. At enormous scales and low energy, certain solutions to Einstein's equations predict that space-time might naturally drift toward configurations that are unstable in higher-order quantum corrections. In plain terms, the universe could become so smooth, so flat, so empty, that the geometry itself becomes sensitive to fluctuations. A tiny irregularity, imperceptible in any other era, could grow into a new region of extreme curvature. And if that curvature grows the right way, it could inflate into a fresh cosmos with its own distinct expansion. One of the most intriguing ideas involves the fate of the cosmic horizon. As dark energy pushes everything apart, the horizon becomes the defining feature of space-time. It marks the boundary beyond which nothing can be known. But horizons are thermodynamic objects. They have temperature, they radiate, they carry entropy. As they evolve, they subtly reshape the way information is stored in the universe. And when the horizon eventually decays, something predicted in certain quantum gravity models, the universe loses its boundary conditions. In losing them, it becomes free to adopt new ones, and that freedom can act as the beginning of a new cosmological epoch. The end of the horizon becomes the opening through which new space-time conditions emerge. This idea connects to the suspicion held by some theorists that the universe does not need to collapse into a point to trigger a new beginning. It may be enough for it to reach a regime where its governing equations shift in character. A place where the familiar four-dimensional fabric loosens, where extra dimensions, if they exist, can move or flex. A universe in its death throes is not an inert object. It is a system approaching a state where the constraints of its early life no longer apply. And once those constraints loosen, even slightly, transitions become possible. Consider the possibility of contraction as well. If dark energy is not truly constant but merely persistent, it could decline on scales vastly longer than the age of stars. When it finally weakens, gravity may once again assert itself. The universe, having expanded for unimaginable eras, could then begin to contract. The return towards density would heat what remains of matter and radiation. Slowly at first, then rapidly. If the contraction continues to extremes, quantum gravity may intervene before a singularity forms. Some models show that spacetime will reach a minimum allowable volume and then rebound. Not in an explosion, but in a reversal of curvature that begins expanding anew. The Big Bang becomes the outward swing of a universe that had reached its inward limit. But perhaps the most curious scenario involves black holes. In the present era, they anchor galaxies and govern stellar remnants. But in the dying universe, after all matter has evaporated and all structures have dissolved, the last black holes become the final active agents. Their Hawking radiation drips out over unimaginable timescales, carrying with it the encoded information of everything they devoured. And when the very last black hole evaporates, the energies involved approach scales where normal space-time descriptions collapse. A few theoretical frameworks suggest that this final evaporation might produce conditions akin to a new cosmic seed. A moment so dense and energetic, so close to the Planck regime, that it can no longer remain part of an otherwise empty universe. It detaches, expands, begins again. These ideas, different in their details but similar in theme, all converge on a remarkable truth. The death of a universe is not a singular concept. It is a period, a long, quiet transition, a soft descent toward a state where deeper rules begin to surface. In that silence, the universe becomes sensitive to fluctuations, instabilities, geometric tensions, quantum transitions, phenomena that were always present but overshadowed by the bright chaos of youth. Taken together, they point toward a universe that cannot simply fade forever. Something in its mathematics resists final stillness. Something in its fields refuses complete quiet. The emptier the universe becomes, the more prepared it is for a change it cannot avoid. And so the question shifts again, from how a universe ends to why it begins. Why does reality refuse to remain empty? Why does structure return in new forms? Why does silence so often precede creation? No one has the final answer. But the best physics suggests something profound. The end of a universe is not a boundary. It is a state. And states, no matter how extreme, are fertile. The next universe does not wait for permission. It emerges from the conditions the previous one left behind. Conditions shaped over trillions of years until they become delicate enough, quiet enough, open enough for something new to take shape, surrounded by the long, slow echo of everything that came before. What remains of the universe in that distant, dim epoch is not a place of drama, but a place of profound restraint. Everything that once defined cosmic history, fusion in stars, gravitational collapses, galaxy formation, particle interactions, has slowly extinguished itself. What endures is not the brilliance of astrophysics, but the faint hum of the laws underneath, the quiet scaffolding that has always held everything together. And now, without the noise of galaxies and radiation, that scaffolding becomes visible in ways it never was before. Imagine a universe stretched so thin that a single cubic light-year contains barely a handful of particles. Imagine temperatures drifting just a fraction above absolute zero. The cosmic background, once bright with newborn heat, has long since softened into wavelengths so enormous they barely count as radiation at all. Everything that once burned with complexity has slowed, cooled, dissolved into something like mathematical stillness. But that stillness is not dead. It is pregnant with subtlety. At this stage, the universe is almost entirely governed by fields: Higgs fields, inflaton remnants, gravitational potentials, and the vacuum energy that defines the very shape of space-time. And the vacuum, far from being nothing, is a deeply structured thing. Its structure is not visible, not tactile, not directly measurable with the sorts of tools humans can imagine, but in its quiet fluctuations lies the entire possibility of the future. What the universe becomes next depends entirely on what these fields can still do when nearly everything else has vanished. One of the strangest consequences of quantum theory is that emptiness is restless. Even a perfect vacuum contains energy. Fields quiver, even in total darkness. These quivers are small, too small to matter in the young universe, overwhelmed by hot plasma and violent interactions. But in the extreme stillness at the end of time, those tiny fluctuations are the only movements left. A shift that would have been insignificant billions of years earlier could now carry enormous weight. A rare fluctuation, one that bends space-time just enough, might create a tiny domain with a slightly different vacuum energy, and inside that domain the rules could change. If those rules favor inflation, even for a brief instant, that tiny patch would expand at fantastic speed, faster than light, not by pushing through space but by creating new space within itself. To the dying universe outside, the event would be invisible, swallowed by its own vastness. But to the region inside, that inflation would feel like a big bang. A bright, hot beginning, a rush of expansion, a flood of particles condensing into the earliest forms of matter. The universe that gave birth to this event would never see it. The newborn universe would never know its parent. But the transition would link them in a way not easily described by ordinary language. One cosmos dissolving into cold emptiness, another erupting into heat and brilliance. Two vastly different realities connected by a single quantum shift. But this is not the only path a dying universe could take. Consider the possibility that dark energy, the mysterious force accelerating cosmic expansion, might not be constant forever. If its value changes slowly over impossibly long times, the balance between expansion and gravity could shift. After an era of rapid expansion, the universe might settle into a slower, more delicate period. Over longer spans still, gravity might reclaim dominance. What begins as gentle slowdown becomes a gradual pull inward. Structures that had been drifting apart with increasing distance begin to creep toward each other again. Eventually, the cosmos might enter a period of contraction, long and slow at first, then increasingly accelerated as density rises. During such a contraction, the dynamics change dramatically. Radiation warms. The remaining particles, few though they might be, gain energy as space compresses. Quantum fields behave differently under contraction than expansion. And, as the universe approaches densities that echo its earliest moments, the old rules begin to bend. Classical physics predicts a singularity, a point of infinite density. But quantum gravity suggests otherwise. Loop quantum cosmology, in particular, posits that space-time has a smallest possible unit of volume. It cannot collapse indefinitely. When it reaches that minimum, gravity changes sign, becoming repulsive instead of attractive. The universe rebounds. What was collapse becomes expansion. This bounce would not be a replay of our Big Bang. It would be the emergence of a new universe, shaped by the quantum state of the cosmos at the moment of maximum compression. Patterns, symmetries, or entanglements from the old universe might influence the initial conditions of the new, not through matter or memory, but through the mathematical state of space-time itself. A cosmic rebound could carry forward faint imprints, subtle fingerprints that shape the next world in ways barely detectable. But the universe may not need to compress at all. It may instead reach a threshold of smoothness so absolute that its geometry becomes unstable in a quiet, precise way. As the cosmos stretches under the influence of dark energy, its curvature approaches perfect flatness. In this state, space-time becomes something like a sheet pulled taut across an enormous frame. When a sheet is stretched tightly enough, even the smallest vibration can create patterns that ripple far beyond their origin. Similarly, an ultra-flat universe becomes sensitive to tiny distortions in its underlying fields. a slight change in the Higgs field, a minute quantum fluctuation, a tiny patch of space beginning to behave differently. Any of these effects could create an isolated region where the rules of physics shift. And once shifted, the region might inflate into a new cosmos. The shift need not be dramatic. It could be subtle, like a grain of sand that suddenly dislodges a hillside that has balanced for eons. The universe may end not with collapse or explosion, but with a quiet failure of stability, an instability so small that it escapes detection until the moment it triggers the birth of something new. For others, the path to rebirth lies in higher dimensions. In brain cosmology, our universe is a three-dimensional surface floating within a larger multi-dimensional arena. Two such brains may drift apart for ages beyond comprehension. In the era of the universe's death, when matter is nearly gone and the brains move gently, almost imperceptibly, tiny forces in higher dimensions could begin to draw them together. When they finally make contact, energy floods into the collision region, producing conditions nearly identical to those of a Big Bang. The brains separate again, launching a new cycle of cosmic evolution. In this view, the death of our universe is simply the time between collisions, a long, quiet glide through higher dimensional space before the next impact forms the next cosmos. Some physicists look instead to black holes, not just as engines of destruction, but as potential gateways to internal expansions. Classical theory says that black holes end in singularities, but singularities are artifacts of incomplete physics. Quantum gravity is expected to soften them. If within a black hole's core space-time continues inward, not to a point, but to a region capable of rebound, that rebound might create a new expanding region, a new universe. The black hole's horizon becomes a boundary between two cosmic realms. Our universe sees matter falling in. The internal universe sees a blossoming of new space-time. The death of our cosmos, then, plays only a partial role. A universe can spawn new universes throughout its lifetime, long before its final breath. Yet the deepest idea of all may be this: the end of a universe is not a single moment or a single mechanism. It is a long process of simplification. Complexity decays, structures dissolve, energy thins, dimensions relax, boundaries weaken, fields approach equilibrium. And it is precisely in this approach toward simplicity that the universe regains the freedom to change. Where matter once enforced limits, emptiness now permits transformation. Where radiation once obscured subtle effects, darkness now amplifies them. The universe becomes a canvas cleared of all but its foundational rules. And in that cleared space, those rules can express themselves in ways they could not before. The Big Bang of the next universe may arise from a quantum transition, a dimensional shift, a collapse and bounce, a brain collision, or something stranger still, something we have not yet imagined because it lies buried beneath the noise of our current cosmic era. But the principle emerging from all serious theories is the same. Endings in cosmology are conditions, not barriers. An old universe does not fall into nothingness. It falls into a state where the constraints that shaped it loosen just enough for the deeper machinery of reality to activate again. And when that machinery activates, whether through the whisper of a vacuum fluctuation or the final drift of a higher dimensional brain, the result is the same in essence: the quiet ignition of a new reality, rising out of the stillness left behind by the one that came before. In the dimmest era of an aging universe, where even gravity seems tired and matter thins into irrelevance, the cosmos enters a phase that no human language is well equipped to describe. It is not death in any familiar sense. It is not silence either, even though almost nothing moves. It is a state where the universe becomes more like a blueprint than a place, a framework rather than a stage of events. What remains is the deep architecture of physics itself, stripped of light, stripped of structure, stripped of all but the most fundamental behaviors. It is in this final era that something extraordinary happens. The laws of physics no longer compete with the chaos of stars and galaxies. They no longer work around the noise of heat, or the push and pull of matter, or the wild irregularities of a young cosmos. Instead, they act alone. They act in purity. And when the laws stand alone, without obstacles or distractions, they begin to reveal patterns that were previously buried beneath the brightness of creation. Consider the vacuum, the very thing that seems like nothing. In truth, it is a kind of canvas woven from countless fields that ripple even when they appear perfectly still. These ripples were always present, even at the dawn of time, but they were faint compared to the roar of early expansion. Now, with all that noise gone, the faintest tremor in the vacuum becomes meaningful. A shift so minuscule it could never influence the young universe might now become the catalyst for transformation. Quantum theory predicts that the vacuum is never perfectly stable. It only appears stable because the universe is so chaotic and energetic that the vacuum can hide its fragility. But as the universe stretches and cools, as entropy pushes it toward perfect uniformity, that fragility becomes more pronounced. A small variation in the vacuum energy, something that resembles a shallow wrinkle in the fabric of reality, could slip into a lower energy state. Such a slip would not be gentle. It would release energy in a form so dense and intense that it could create a new space-time region with entirely new laws. Inside that region, the temperature would rise to levels trillions of times hotter than the core of any star. Particles would condense out of quantum fields. Time would begin to differentiate from space. Forces would separate. Expansion would roar outward. This is the essence of a Big Bang, not a blast within an existing universe, but the birth of space-time itself. To any being within that region, nothing outside it would be visible or meaningful. The old universe would not appear as a past. It would not appear at all. Another path to a new beginning lies in the possibility that the universe, after growing unimaginably large, becomes geometrically fragile. In general relativity, space-time is not a fixed grid. It is elastic. And like any elastic structure, when stretched too far, it becomes vulnerable to folds, wrinkles, or reorganizations. A universe expanded for octillions of years could accumulate these minute tensions, subtle as they might be. Over long enough timescales, even the tiniest geometric imperfection can grow. And, under the right conditions, those imperfections may cause entire regions of space-time to reconfigure themselves into new domains with different curvature, different expansion rates, and ultimately different physics. Such a reconfiguration would not resemble the dramatic collapse that once created stars. It would occur quietly, imperceptibly at first. But once a region begins to curve inward or outward with sufficient intensity, the process becomes unstoppable. The transition is swift, expanding a small imperfection into a full-blown new universe. Other theories imagine a cosmos that does not fade forever, but slowly changes the balance between its forces. Dark energy might evolve. Gravity might weaken or strengthen over vast ages. If dark energy diminishes even slightly, the runaway expansion could reverse. Galaxies, too distant to ever see one another again, would begin to drift inward. The universe might enter a long contraction. Temperature rises, density increases. Radiation becomes intense again. And as contraction accelerates, the cosmos begins to resemble its earliest moments in reverse. Approaching densities that classical physics cannot describe, quantum gravity steps in. In the models proposed by loop quantum cosmology, space-time does not permit infinite density. Instead, it reaches a smallest possible volume, one that acts like a kind of spring. When contraction reaches this limit, space-time pushes back. A bounce occurs. Outward expansion begins. This is not a repeat of the previous Big Bang, but a new chapter emerging from the last moment of the old universe's life. Yet, another possibility comes from the idea that our universe is a surface, what physicists call a brain, floating in a higher dimensional space. If another brain exists parallel to ours, their slow motion through higher dimensions could set up cycles of approach and separation. When the brains drift apart, the universe cools and expands into a long, quiet darkness. When they drift closer again, after timescales so immense the mind cannot hold them, their collision ignites a storm of energy. From that storm, a new universe unfolds. No collapse is required, no vacuum shift. Just a slow drift through a larger dimensional sea until contact is made. Even black holes hold possibilities. In the late universe, they are among the last structures to persist. Over breathtaking timescales, they evaporate one quantum at a time through Hawking radiation. But near the final stages of evaporation, conditions become extreme. Density climbs, temperatures spike, and classical physics loses its grip, replaced by quantum gravitational behavior that we still barely understand. Some theories suggest that in those final, furious moments, space-time could pinch into a new configuration entirely. On our side, the black hole disappears, leaving behind a whisper of radiation. On the other side, the collapse may have triggered a new expansion, a new universe blooming from the place where our own space-time folded inward. In every scenario, the pattern repeats. The death of a universe is never an absolute termination. It is a transition into simplicity. And that simplicity makes the universe more sensitive, more dynamic, more capable of transformation. In youth, the cosmos is too chaotic to permit delicate processes. In middle age, it is too structured. But in its final centuries, measured not in years, but in incomprehensible spans, the universe becomes light enough, calm enough, balanced enough for deeper mechanisms to act. It is in this deep quiet that physics returns to its most fundamental expressions. The vacuum remembers how to shift. Geometry remembers how to bend. Dimensions remember how to move. Fields remember how to spark. The things that once required enormous energies now require only stillness. A universe that has spent trillions of years expanding and cooling might, in its final breath, become the most responsive it has ever been. The smallest tremor, the faintest instability, the tiniest fluctuation might rewrite the entire structure of space-time. And from that rewriting, whether it arrives as a bounce, a quantum tunneling event, a brain collision, a vacuum reconfiguration, or something that has no name yet, a new universe will come into being. Not because the old one wills it, not because anything survives in the emotional sense, but because reality itself never permits its deepest structures to remain inert forever. Even in a universe stripped of stars, stripped of matter, stripped of heat, there remains a tension in the rules, a readiness, a susceptibility, a kind of cosmic breath held for a very long time. When that breath is finally released, something extraordinary follows. A new beginning that knows nothing of the quiet that came before, yet depends entirely on the fact that such quiet existed at all. In the unimaginable calm of an ancient cosmos, where space-time has stretched into a thin and nearly featureless expanse, the universe reaches a point where its own vastness becomes its defining characteristic. Distances so large that nothing can meaningfully communicate. Temperatures infinitesimally above absolute zero. Particles so rare that entire galaxies have fewer constituents than a single breath of air. In that stillness, the universe feels almost hollow. But the hollowness is deceptive, because beneath the fading echoes of matter lies the one quality that has never vanished across the lifetime of the cosmos. Structure. Not the structure of galaxies or atoms, but the structure of the laws themselves, the deep architecture of fields, symmetries, and mathematical relationships that govern what can and cannot exist. These laws do not erode with time. They do not weaken when stars die. They do not vanish when matter decays. They remain, silently influencing every subtle fluctuation that stirs in the dark. And it is precisely here, in the era where everything else has drained away, that those laws begin to reveal what they can do when left unchallenged. When the universe is young, the fundamental forces are constrained by the overwhelming presence of matter. Heat floods every corner of space. Density shapes every interaction. The fields that underlie reality do not have the freedom to reach their deeper configurations. They are held in place by the noise and weight of the early cosmos. But a universe near the end of its life no longer suffers from that confinement. The absence of matter becomes a kind of permission, a lifting of constraints that allows the deeper layers of physics to move in ways they never could before. And this invites an astonishing possibility. Perhaps the laws of physics behave differently when the universe becomes nearly empty. Not different in an arbitrary way, but different in a deeper, quieter sense. Shifting into behaviors that only emerge when space is stretched thin and uncontaminated by complexity. This shift could take many forms, each one subtle and slow, unfolding on timescales that dwarf all astronomical events. For example, the value of the vacuum energy, the energy of empty space, might itself change ever so slightly as the universe ages. Dark energy, which now drives cosmic expansion, might not be constant forever. Over unimaginable epochs, it could drift toward a different value, one that alters the balance between expansion and contraction. Even a small change, imperceptible today, could eventually tilt the entire cosmos toward a new evolutionary path. If dark energy weakens, expansion slows. The universe's geometry becomes less stretched. Gravitational influence increases. What once drifted apart may begin to approach again. The cosmos might reverse its course, entering a period of contraction so slow it would go unnoticed by any being living in its early ages. Over eons upon eons, the contraction accelerates, heating the relics of matter that remain. If the contraction centers into a collapsing region, the density could reach a point where quantum gravity refuses to allow further compression. At that threshold, the universe might rebound, turning contraction into expansion. A new space-time would pour outward, not a repeat of the previous universe, but a new phase governed by the quantum state created in the contraction's final moments. But contraction is only one path. The opposite scenario is equally profound. If dark energy strengthens or remains constant, expansion becomes eternal. Galaxies disappear beyond horizons. Particles disperse forever. Even black holes eventually evaporate. The universe tends toward perfect smoothness, a uniform field of near-nothingness, and in that uniformity lies the potential for the vacuum itself to transform. This transformation is not a collapse or an explosion. It is a quiet shift in the underlying field configuration. Imagine the universe's vacuum like a fabric woven from countless microscopic threads. In its youth, the fabric is heavy and taut with energy. In its age, it becomes light and loose. A tiny wrinkle, a small tension, a microscopic fluctuation might cause the fabric to snap into a new arrangement. That snap, though microscopic in origin, could unleash a region of new physics, one that immediately expands at extraordinary speed. From the outside, nothing appears to happen. From the inside, a new universe is born. Another route to rebirth comes from the geometry of the universe itself. As space grows, its curvature becomes increasingly flat. A perfectly flat universe is delicate, not because it can tear, but because flatness amplifies the influence of tiny distortions. A universe nearing perfect flatness may become prone to sudden shifts in how its dimensions behave. In string theory, for example, the shape of compact dimensions determines the physical constants. Over extremely long ages, those curled dimensions might drift, slowly altering their geometry. A small shift could release a flood of energy, reconfiguring space-time and creating a new domain with different laws. This sort of reconfiguration is not violent. It resembles the slow movement of tectonic plates beneath a quiet ocean, imperceptible until the moment the tension becomes too great. When it releases, a new landscape forms. Not a restoration of the old universe, but a fresh beginning carved from the underlying geometry. And then there is the possibility that the next universe emerges from within the remnants of the current one. Black holes, after eons of evaporation, become some of the last active objects in the universe. Their late-stage behavior pushes physics beyond the limits of general relativity. As they evaporate, their shrinking horizons probe energies close to the Planck scale. In that extreme regime, space-time may behave in radically non-classical ways. The interior of a black hole could become a place where space-time reconnects with itself, where new regions branch off, free from the grip of the parent universe. In this picture, each black hole is less an ending and more a doorway, a seed that might blossom into a new cosmos once it separates entirely from ours. Whether through quantum fluctuations, geometric shifts, dimensional movements, vacuum instabilities, or the quantum cores of black holes, a remarkable principle emerges. The universe cannot simply fade into perfect stillness. Its mathematical structure does not permit it. The vacuum is active. The fields never reach absolute rest. Geometry cannot maintain perfect balance indefinitely. Quantum effects become increasingly significant as everything else drains away. The death of a universe, then, is not decay into oblivion. It is the gradual exposure of the deepest layers of reality, the layers that do not reveal themselves until the cosmos becomes cold enough, empty enough, simple enough for subtle forces to take command. Somewhere in that vast stillness, the laws begin to shift in ways imperceptible to the early universe. A field reaches a threshold, A geometry becomes unstable, a dimension moves, a fluctuation exceeds a critical size, and a point, so small it has no size in ordinary terms, begins to expand into a new space-time. That expansion is not caused by the death of the old universe, it is allowed by it. The old cosmos becomes an incubator without even knowing it, a place where silence becomes fertile, a stage cleared so thoroughly of complexity that the underlying equations regain the freedom to generate something new. And in the very moment when the old universe becomes too empty to matter, a new universe lights itself into existence, carrying forward not the memory of its predecessor, but the consequences of the physical state that predecessor left behind in its final breath. When the last traces of structure finally dissolve, when space-time itself grows thin with age, the universe does not vanish. It reaches a clarity it has not known since its earliest moment, a clarity so complete that only the deepest rules remain: symmetry, geometry, the quiet pulse of quantum fields that never truly fall silent. Those rules linger long after matter has gone, long after radiation has stretched into oblivion. And in that state of perfect simplicity, the universe enters a condition from which it can do something extraordinary: begin again. No single mechanism defines this renewal. It might come as a quiet shift in the vacuum, where emptiness slips into a new configuration and ignites a fresh domain of space-time. It might arise from contraction pushed to its limit, rebounding through quantum gravity into expansion. Might appear through dimensions drifting in higher spaces, brushing into a collision that births a new cosmic fire. It could emerge from the final trembling of a horizon dissolving into quantum foam, or from a black hole's last whisper as its core gives rise to a new interior universe. Every path leads to the same profound truth. The cosmos does not die the way living things do. Its ending is a threshold, a thinning of constraints, a slow surrender of complexity until the fundamental architecture becomes free to reshape itself. And from that reshaping, subtle, quiet, inevitable, the next universe is born. Not from the destruction of the last, but from the conditions the last created by fading. A universe ends not with finality, but with a return to the groundwork from which beginnings emerge. Stillness becomes possibility. Simplicity becomes potential. Silence becomes the soft boundary across which a new reality finds its first breath. If this quiet journey brought you a moment of calm, a gentle like or a soft tap on subscribe truly helps keep this calm corner of the universe glowing. And tell me, where in the world are you listening from tonight? Rest well until our next quiet journey.